Dr. Jayawardhana from the University of Toronto. He's here as a guest of the astrobiology school. And he's in fact also part of an effort to start a similar astrobiology collaboration in Canada, right?
Yeah, we're not anywhere near as far as you guys are, but we sort of started the initial discussions, yes.
Yes. Okay, and he also, so he is on a 3-year sabbatical or something. Well, he was, as he was preparing for his first-year sabbatical, he got this Stacy Prize, which gives him 2 years of teaching, basically. So during this first year, he has been to University of Leiden in the spring, in the fall, where we from the astrobiology school also had our fall excursion, and so you were there in Leiden at the same time as us. And he's also spent some time writing his new book, which he just recently finished, and it's going to be published in half a year or so, we hope. It's called Worlds Beyond.
Yes.
Yeah. Anyway, today he's going to talk about extrasolar planets and their diversity. So, please.
Okay, thanks very much. Thanks, Alexis. Since this is quite a diverse audience, feel free to stop me anytime in the middle and ask me to explain if I get into the astronomer's lingo too much. But I'll try not to keep it to a minimum. As many of you have probably heard a lot about extrasolar planets in the last decade or so, it's one of the most exciting and active areas in astrophysics. So I'm not going to cover it all, but I am going to sort of remind you a little bit that it wasn't so long ago that we really were very clear on the difference between stars and planets. Even biologists knew what the difference was, right? And now even astronomers don't quite, because it's gotten much messier. And also there used to be 9 planets, and a few years ago we lost one, and that's because of all these so-called Kuiper belt objects, or these sort of dwarf planets that are being discovered beyond the orbit of Pluto. And not everybody that are about the size of Pluto have moons, and share many of the other characteristics. I'm not going to go into details, except that many people, as you remember, were quite unhappy about the demotion of Pluto into a dwarf planet. The only good thing about it, I think, is actually there are 4 different states in the US that passed state resolutions reinstating Pluto. So at least these state legislations learned something about astronomy for half an hour or something like that. They gave all kinds of reasons, including that people in California would be disturbed by the missing planet on their astrological beams. But now we have 2 different classes of planets in our solar system, and we expect in particular this class of dwarf planets to grow by the dozens. So this is the reason that a whole new category was found, was defined before the school children would start complaining to us about having to memorize the names of 50 planets in the solar system. But we do have even more already identified, many more beyond our solar system, and this is what I'm really going to be talking about. The count now is over 450, and this is in less than 15 years. This fall will be the 15th anniversary of the first extrasolar planet that was announced around a solar-type star. So we're likely to get to 500 by then. So 500 in 15 years is not a bad pace of discovery after many decades of talking about them and having false claims that had to be retracted later. This is just kind of a snapshot of some of these planets to give you a sense that in terms of separation from their star, on this axis, the Earth would be at 1 astronomical unit. Many of these planets that have been discovered so far are really in star-hugging orbits. They're really very close to their parent stars. We call these hot Jupiters, and I'm going to talk about them a little bit. And by now, we're starting to find some lower mass planets that are also in very tight orbits. And then a number of multiple planet systems have been found, and a handful of Jupiters and Jupiter-like orbits have also been discovered. And the vast majority of these, still I think close to 3/4 of these planets have been discovered by the method, the radial velocity method or the Doppler method, measuring the velocity of the star to in for the mass, in for the presence and the orbital characteristics of the planet. This is the first planet discovered around 51 Pegasi in 1995, really sort of opened up this revolution, and it's continuing, and this method is still the one that's responsible for close to 3/4 of the planets. But this is likely to change quite soon, in the next couple of years. And when you have multiple planets, like around the star Upsilon and Andromedae, you get these sort of multiple periods that you can see in these Doppler velocity curves. So in this case, the innermost planet has been removed, so you can still see 2 different periods due to the 2 different planets. Because people often ask in this wobble method, how do you tell that there's more than one planet? The most impressive thing about this Doppler technique is the way in which the precision of measurements has improved over the years. So this is in time, starting in 1990 until today. What is the lowest mass planet that one could detect with the Doppler method has gone from Jupiter down to a couple of Earth masses. And HARPS is this Geneva Observatory team's instrument that's located at a telescope in Chile now. That is the world's best and world's most stable and best instrument for making very precise radio velocity measurements. So they're making measurements routinely now at about 1 meter per second precision. So this is the kind of wobble that is being measured. In fact, you can walk 10 times faster than this. So that's the level of precision that's being achieved with the radio velocity technique today, and that's allowing astronomers to detect planetary systems like this. This is the M dwarf nearby red dwarf star with 4 low mass planets. The innermost planet is just under about 2 Earth masses in minimum mass. The outermost one is 7.1 and might even actually be in the habitable zone for this star because this is a lower mass star. The distance at which water would be in liquid form is shifted in closer to the star. This is for the solar system, where the Earth is in the middle of the habitable zone. For Gliese 581, maybe the outermost planet is just barely on the edge of the habitable zone. Whether it's actually habitable, whether water can actually be in liquid form, of course, depends on many things other than just the distance to the star. That's a very simple definition, but depends also on the atmosphere of the planet, the composition, how much of a greenhouse effect is in play, for example. It could bring it right into the thick of the habitable zone. But that's quite interesting and exciting from an astrobiological point of view. This is really just a marginal first case, but the idea is that these kinds of objects will grow quite a bit in the next few years. The second technique that has worked, I'm sure you've heard about as well, is finding planets through transits. When a planet passes in front of the star, like Mercury and Venus do, this is in our own solar system against the sun, you can see a planet transiting in front. We can't quite take this kind of picture for extrasolar planets because we don't see stars like that. We see stars as points of light, but we can see when a planet passes in front of the star dimming for a very brief period of time, usually a few hours, when it's a hot Jupiter, dimming by about 1 to 2% in brightness, and then it comes back to its normal brightness, and we can observe these transits. This is the transit observed in a follow-up observation with the Hubble Space Telescope for the first transiting planet discovered back almost 10 years ago now, and that's a 1.5% dip. The size of this dip is telling you how big a planet is, because the bigger the planet, the bigger the fraction of the star's face that it would cover. So smaller planets will make smaller transits, bigger planets will make bigger transits. Of course, the technique is therefore biased towards finding bigger planets. And the closer in a planet is to the star, the higher the chance that you will catch it in an edge-on orbit to be seen in transit. Planets that go in polar orbits, for example, you'll never see in transit. So the chance of transit increases the closer in a planet is. By now, the number of transiting planets is over about 60, and 2 of them are in what's called the super-Earth category, planets that are between about 2 to 10 Earth masses, and potentially at least could be rocky in composition. One thing I find really cool about this technique is that most of these transiting planets, in fact, half of them have been found with just one particular experiment that use little telescopes like that. These are somewhere between 10 to 30 centimeters in diameter. So these are smaller than many of the best amateur telescopes that exist. And they are good because they're small, they cover a wide swath of the sky, they monitor tens of thousands of stars at the same time, bright stars mostly, and then they try to catch a handful where you see the planet in transit. So this is a technique that's really blossoming now, and I'll come to it at the end of the talk, partly because now it's being done from space with the Kepler satellite. So that can achieve much higher precision and therefore much lower, much smaller planets.
So this was Mercury transit in 2000 and some? No.
This is from a few years ago.
Right.
Yeah, the most recent one was Venus in 2004.
Yeah, but that would look bigger than that.
Yeah. The thing you get from this technique is the size of the planet from the size of this dip, which is really interesting, especially if you can combine that with a radial velocity measurement of a mass of the planet. If you combine the mass and the size, you can actually get a density for these planets. So here's a slightly complicated plot, but this is showing for a number of transiting planets, for Jupiter planets, the mass of the planet in Jupiter masses, and the radius of the planet in Jupiter radii. And here's Jupiter, and here's Saturn in our solar system. Okay? And this is where the extrasolar planets fall in this radius, mass radius diagram. And what does this show you? Well, some of these are not too different from Jupiter and Saturn, but a handful of these are huge. So for the same mass, half a Jupiter mass, they have a radius that's 1.4 times the size of Jupiter. So 40% bigger than Jupiter at half a Jupiter mass. So that's telling you that these planets are really bloated, that they're really bigger than they would be if they had the same structure and composition as the giant planets in our own solar system. So in some of these cases, these planets are so close to the star, they are irradiated quite strongly by the star. You expect extra radiation and bloating due to that. And in some cases, the closest planets, again, you also have tidal interactions between the planet and the star. And you expect tidal heating to be an extra source of energy, and maybe planets get bloated because of that. But for these biggest of them, the most bloated of them, even accounting for those two sources of energy doesn't seem to be enough. So modelers of planet interiors are having a hard time explaining how planets can be that big, even when they're so close to the parent star. So this is the kind of thing that you're starting to do. This is not quite yet for Earth-like or rocky planets, but certainly for giant planets, instead of having two in our solar system, now there are dozens to do comparative studies with. So that's where sort of the field is going. Now, of course, we are much more interested in doing the same thing, measuring the radii and therefore inferring the density for lower mass planets. So for Jupiter, we think we have the denser structure like that with a small core that's maybe 10 to 15 Earth masses at most. Now, what about lower mass planets? You can have a lower mass planet, the same mass planet, to be big or small, depending on what it's made of. So if you have primarily, for example, an icy super-Earth, it would have a much larger radius than if it was a much rocky, higher density planet. So can you distinguish between these two possibilities? That would be very important and interesting, especially for an astrobiological point of view. You could do that if you had a mass measurement and a size measurement. At least you could infer whether it's dense or low density. And this has been done so far for a couple of these low mass planets, and there's at least one that is recognized as the first definitive detection of a rocky extrasolar planet. So this is a planet that was actually discovered through transit method. Here's the transit dip observed with the Corot French-led satellite. So they had a size first, but it took a long time to get a mass because the star is pretty far away and therefore faint. They couldn't do very good spectroscopy. With a lot of effort, they were able to make a radial velocity measurement and derive that its mass is about 5 Earth masses. So if you have that radius and that mass, it implies this planet has a density that's about similar to the Earth. So this is the first identification of a rocky planet outside the solar system in a definitive way. Now the downside of it is, of course, it's incredibly hot. This is one of these really hot super Earths. So its density is right, but the location is way too close to the star to be supporting liquid water, for example. So it's not ideal for that, but it's at least one of the steps we need if you're looking for other Earth-like planets. Transits are also really interesting, not because only because you get some idea of the density of the planet. But in fact, you can do a lot better than that. You can start to make cleverer and more precise measurements, for example, to probe the atmosphere of these planets. So here's what here's the setup we have. You have a star and this planet transiting in front of the star, and I talked about the planet blocking the light of the star, but in fact, if you think about it a bit more, in a bit more detail, some of the starlight actually skips through the atmosphere of the planet before reaching us, for example, reaching the Hubble Space Telescope in this diagram. That means when a planet is in front of the star, a little bit of that starlight gets imprinted by the absorption due to molecules in the planet's atmosphere. So how do you measure that? Because it's a very, very small decrement in particular lines in the spectrum. Well, you do that in a differential way, which is the way astronomers really do anything, because it's much easier than doing absolute measurements. So you make a measurement when the planet is in front, and then you make a measurement when the planet is not. And you subtract one from the other, and the little bit that's different must be, the extra absorption must be due to species in the planet's atmosphere. So the first measurement of this was done actually quite a while ago, almost 10 years ago now, for the first extrasolar planet, where people were able to detect a little bit of extra sodium absorption in the spectrum of the star due to the planet. So this is the first detection of a planetary atmosphere. Okay, it might not be incredibly exciting because it's a boring species like sodium. Maybe a chemist will tell me actually it's much more interesting than I think it is. But at least it's sort of, direct measurement of a planet's atmosphere. Now, the same kind of technique you can use elsewhere if you have the right instruments to detect all kinds of other things. So this was the first tentative detection of water in the atmosphere of our extrasolar planet. It's not a very compelling detection. So in the background is a model spectrum of water in the mid-infrared portion, going from sort of a few microns to 8 microns. And then these are 3 differential measurements people made at 3 different wavelengths to show that there is indeed a decrement in the flux at exactly the right place, to expect that this is due to water, that there's water in the atmosphere of this planet that's absorbing and therefore depressing its light at this wavelength relative to over here, for example. There's actually, I don't have a plot of it right now, there's a better, a more secure detection in a different planet recently, just in the last year or so. So, but this is the idea, that this is a technique that during transit you can make these absorption measurements due to molecules in the planet atmosphere. It's been done now for water and for methane and for carbon dioxide.
What causes the large error bars in the wavelength direction?
Well, so for one thing, these are fairly broadband filters.
Yes.
Right? So that's not ideal. You really want a spectrum or a lot more narrowband filters. So one is the width of this is simply indicating the width of the filter. Right? And also the precision. There's lots of calibration issues with the photometry. This is a Spitzer Space Telescope measurement. There's this messy thing.
Would there be more filters available, or they don't exist?
They don't exist in these existing telescopes.
Yes.
But this is particularly in the mid-infrared portion. The other methane and CO2 measurements I mentioned are actually with a low resolution spectrograph on Hubble with NICMOS instrument. So there actually it's a bit better coverage. Exactly. So you can be a bit more secure. And also there's a fourth. There is one other filter that could have been used that wasn't used for this one, but was used for the more recent measurement. Yeah. So you can get better constraints. But the idea is that the point being that you can do these kinds of during transit absorption line measurements in spectroscopy. But that's not all. You can also do, if the planet is passing in front of the star, there's also a good chance it will pass behind the star some of the time. If the orbit is inclined edge on from our point of view, there's a high chance it will also go behind the star. So some of the time you get the star plus the planet, and some of the time you get the star because the planet is behind the star, completely hidden away. And then if you can take the difference between these two, you can actually kind of measure the thermal emission from the planet itself. Right? The difference between this and this situation is the planet. So this is a way of using the fact that the planet hides behind the star for a fraction of its orbit to actually make a measurement of its thermal emission. because what you're measuring is just before the planet goes behind. It's showing you its sort of day side. If the planet is tidally locked to the star, like the moon is with the Earth, it's always showing the same face to its star. Just before it goes behind, I'll have a little graphic that maybe explains the situation a bit better. You can make a measurement of the planet's own emission. And that has been done first with the Spitzer Space Telescope in the infrared, where they see this sort of slight decrement in flux when the planet goes behind the star. This is a much smaller dip than the primary transit. We call this the secondary eclipse. You can see it's pretty crappy measurements. It's just barely enough to say that there is a dip, but the error bars are pretty bad because you're trying to measure a very small decrement. But the secondary eclipse is very cool because, as I said, what you're measuring is thermal emission from the day side of the planet. So imagine the planet is always showing the same side to the star and doing this in its orbit, and just before it goes behind the star, or just as it comes out of the star, what you're looking at is its day side. During the transit, you're looking at its night side, right? Because it's showing its day side to the star. So this is kind of the situation we're in, and what you're measuring is the day side thermal emission. And if that emission is a lot, could imply a much higher brightness temperature than the equilibrium temperature for a given distance between the star and the planet. And if you think you know what the amount of light the star is emitting, then you can determine how much of that flux that it receives on the day side gets transferred to the night side. If it transfers a lot of it through winds, through circulation in the atmosphere, then the day side won't be extra bright. But if it doesn't, if it just receives the flux from the star and re-emits very quickly, before it sort of advances to the night side, then the day side would be incredibly bright. It would be much higher than what you expect for equilibrium brightness temperature. So by just measuring this one side, you can tell not only the day side temperature, but you could tell that how strong or efficient the winds are, or the atmosphere is in circulating this heat to the night side. So I'm not going to go into all of these details, but the point is that with the single measurement of photometric measurement, just the dimming of the brightness of the star when the planet goes behind it, you can learn a lot about details of the atmosphere. And when you do this at different wavelengths, you can probe different depths in the atmosphere of the planet. So you really kind of start to get into atmosphere physics. We talk about absorbers that cause temperature inversions in the atmospheres of these planets. All these details that eventually we would want to do for more rocky Earth-like planets of interest to astrobiology. People are doing it already for gas giant planets, where we see in transit and secondary eclipse. The other thing I'm not going to go into detail is that we could also measure how eccentric or not a planet is very, very precisely by making a measurement of this secondary eclipse. Because if it's perfectly circular, the phase should be exactly 0.5 between the primary and the secondary eclipse. Whereas if it's eccentric, you get a slight offset from that time. Anyway, so I said this has been done from space, and we actually want to do this in near infrared from the ground. So it's been done with IRAC instrument on Spitzer at 4, 8, and 24 microns. But in fact, the planet per micron is actually brightest in the near infrared, for which we could actually try doing this from the ground, and that's what we have done in the last year or so. So this is primarily the work of my student Bryce Kroll for his PhD thesis. He's finishing in about a year. What we have done is to use this 3.5 meter Canada-France-Hawaii telescope on Mauna Kea with a wide field infrared camera with a 4-quadrant array, so that we have a very wide field. We look at stars like that one, a planet-host star with a transiting planet, and then we compare its brightness to 10 of the nearest similar brightness stars. So we're making again a differential measurement, and then we think we can make a precise enough photometric measurement to see the secondary eclipse of these exoplanets, at least for the hottest of them. So this is what we've done, and I'll show you our results. From the ground, it's a lot more messy because we have to deal with variations in the Earth's own atmosphere. That's why we need these comparison stars. So we do a lot of these clever comparisons. And here's the secondary eclipse we measured for this planet called TRES-2, and here's the eclipse measurement in the K-band again in the near infrared for TRES-3. So for two of these planets, their eclipse depths are not very deep, and yet we've been able to measure from the ground And that is suggesting that they have very efficient heat redistribution, meaning if they're actually transferring a lot of their heat to the backside, the side that we don't see, the dark side of the planet. That's why the temperatures are actually, they're hot, but they're not ridiculously hot relative to what we expect, given how close the planet is to the star. So these temperature differences actually, the temperatures are quite similar to the equilibrium temperatures that are expected. This paper was just accepted actually last night. This one is on AstroPH. This should be on AstroPH on Monday. So this is very, very new results. This is a program that it's taken us about 8 months to get the right, to figure out the precision, because it's all dominated by systematics. We're making measurements on the order of, for the astronomers in the audience, our precision is something like 0.7 millimagnitudes for every few minutes. So it's an incredibly high precision measurement from the ground, and the only reason we can do this is in a relative way, because we have 10 different stars. We correct for we do this staring mode thing anytime the star moves around. The flux goes crazy at this level, so we really need to make very careful measurements. But contrast these two, if you can remember that for a second, with these two planets. Here the eclipse depth is much greater. Okay, and here we're doing it on 3 different near-infrared bands. That's the K band, the one you should compare to, H band, and even we got half an eclipse in the J band. So for these two planets, the temperatures of the day side are incredible. 2700 Kelvin, 2900 Kelvin. This is incredibly hot. This is like, it receives light from the star, re-emits right away, doesn't get a chance to even add back to the night side. So it's really, the day-to-night contrast on these two planets must be huge. We're not directly measuring the night side temperature, but just from the day side temperature, for them to be this high, that implies they're really poor at circulating the heat throughout the atmosphere. So with this pretty, in some sense, once we've done it, it's a fairly simple measurement, right? It's just flux. It's measuring the photometry, making photometric measurements very, very precisely over some period of time, before, during, and after the secondary eclipse, and inferring all of these things. Especially for this one, where we have 3 different bands in which we measured it, we can learn a lot about the atmosphere. I'm not going to bore you with all of the details, but if you want, you're more than welcome to talk to me afterwards to talk about the details of planet atmosphere models that we can constrain, what kind of, we can even talk about what kind of absorbers are in the atmosphere, all of these things.
Are you implying that they are locked, tightly locked?
Yeah.
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 No. And the overall trend, is that because they're in a binary? No, why is that?
You mean the overall trend
Yes.
like that? No, that's just the trend over the course of the night. Partly because of the air mass is changing of the star. This is an observation over usually about 5-6 hours. Yeah, I mean at this level of precision, that's why I said we really can only do this in comparison to the other stars, and then correcting for any movements in the position of on the array. Right? You have to account for all kinds of errors. Yeah.
Sorry, a short question, although you referred to, we could talk to you afterwards. Concerning the absorbers you can see at that temperature, is that more than CO?
Yes. So this is where it gets the interpretation. We're being conservative and not saying a lot, but what we are doing is making comparisons to existing models for these planet atmospheres. And as you I'm sure know, that's an art that it's sort of in the early stages, right? Yeah. So
CO, I suppose you see directly. Do you see more?
So there's, for example, some of these models have TIO and VO as absorbers. So at some of these temperatures, they're either too hot or too cold for these to be in condensate form in the atmosphere. They should have actually settled, and we're looking above them. So they can't account for them. So then they, because of that, people sort of then invoke whole different other absorbers to account for the, for example, the I'm trying to remember exactly. I think here the J band is not as deep as we expect, given how deep K and H are. So, for example, from that comparison, one can make inferences about an absorber at the wavelength of the J band observation. So that's the level at which we can do that. But I wouldn't necessarily believe any of the interpretation, except at that sort of 50% level, because it's really through the involvement and interaction with the models that we interpret and there's lots of uncertainties in the models. But one way to really test the models and to compare and to know whether we believe them is to do a large sample, right? Now we've done 4, well, why don't we do 20? So that's what we said. There was a call for large programs on CFHT in February. We submitted this proposal, and just last week found out it got accepted. So in the next 5 semesters, we will get something close to 200 hours of time, and we hope to do at least a dozen more, maybe about 15 more of these. So we'll have somewhere between 12 to 20 exosolar planets with multiple near-infrared measurements of secondary eclipses just in the next 2-3 years. Okay, this is our sort of target list. You can see this is not even 20. So we expect to be able to add to this target list as new planets are being discovered. In fact, one of the Kepler planets, one of the 5 that was announced, in fact actually 2 of the 5 that were announced last January, around stars that are bright enough we could do this technique from the ground. So it's really kind of, especially for those, we can learn a lot because you have the optical coverage, in fact an entire phase curve from Kepler, and then we do the near-infrared. Spitzer has a program accepted by other people to do mid-infrared secondary eclipses. So if you really had the full wavelength range, now we're talking about, characterizing atmospheres. You're starting to, for example, distinguish between reflected light, the contribution from scattered light versus the thermal emission. As a function of wavelength, you can start to make these distinctions. So this is just the secondary eclipses. I'm sure I should have had this little, graphic before to explain. This is what I meant by seeing the day side just before it goes behind, because it's tidally locked, and as it comes to the primary eclipse, we're looking at the night side. This sort of graphic shows you what we mean by these tidally locked orbits of these planets. Now, I was just talking about the primary and the secondary eclipse, but for a couple of these, Heather Knudsen, for example, did the first one. For one of these planets with Spitzer, people were actually able to do the entire phase curve. Not just this and that, but even in between what happens. And then she was able to sort of invert that into a map form and make sort of the first crude map of an extrasolar planet. You see sort of the hot spot, and then the other parts are not so hot, not so bright. Of course, there's almost no resolution in this direction. There's resolution in that direction in terms of that there's a hotter and cooler part of the planet, right? So it's a bit of a fake map in that sense. It's really like a one-dimensional map, not a two-dimensional map. But it's kind of interesting, and with Corot and Kepler, people are going to be doing this all the time, making these phase curve measurements. Just like the phases of the moon, you're seeing different parts of, this is the primary eclipse, the secondary eclipse. Why is it brighter here than here before the primary eclipse? This is, remember, you're looking at the night side. Right? Here you're looking at the day side. Just before it goes into secondary eclipse, it comes out, it's still that you're looking at the bright side, gets fainter and fainter, goes into primary eclipse. So you're really observing the phases of planets like we observe phases of the moon. And depending on at what wavelength you're looking at, you can learn a lot of different things. If it's just reflected or scattered light, it's one thing. If you do it at wavelengths where you see thermal emission, that's a whole another piece of information. Okay. So with all of that, as of about 2 years ago, this is where we sort of stood. This is a log-log plot showing the separation of planets from the star and the masses of the planets in Earth masses. And these are the planets in our solar system. These are the radio velocity detected planets, the transiting planets, a few planets found through microlensing, a few planets found around a pulsar, through pulsar timing, and there's a lot of empty space on this diagram, right? So this is the reason that even with all the techniques that are being successful, I didn't really discuss microlensing, which is interesting but also limited in some ways because you can't do follow-up. We're really biased towards finding planets that are pretty massive, hundreds of times Earth masses, and then pretty close into the star. This is 1 astronomical unit, so most of the planets that have been discovered are still within a few astronomical units of their star, because with radio velocity it takes too long to monitor. With transits, the chance of catching them in transit dramatically drops as you go further out. So there's this whole part of this diagram where the outer planets of our solar system exist, where we really have no information from these techniques. So that's where direct imaging comes in. So I'm going to sort of spend the next 15 minutes or so talking to you about direct imaging, partly because of personal interest. This is the other thing that my group does these days, but also because it's really also the cutting edge in planet detection. So if you really want to understand the full diversity of planetary systems, then you really want the full set of complementary techniques, including direct imaging, because direct imaging is sensitive exactly where these other techniques are not, meaning further away from the parent stars. Unfortunately, it's also biased towards more massive planets just because they are brighter. However, at least in terms of the orbital radii, it's complementary. And then if you have an image of a planet, often you can actually take spectra, and then once you take spectra of these planets directly, separate from the star, you can make a lot of interesting comparisons to models. And if you really want to understand how these planetary systems compare to ours, even for things like volatile delivery or what's going on in the inner solar system, what happens further out also matters. For example, now, some of you might have heard in the last couple of years, there's growing evidence that many of these, even the inner planets, even the hot Jupiters, their orbits are misaligned relative to the equators of their stars. They're misaligned relative to the spin axis of the stars. How do you get that? If planets form in a disk and they migrate through a disk, you wouldn't expect a whole lot of misalignment. And the most recent thing that I read about was in the Epsilon Andromeda system, the two of the three planets may be actually inclined relative to each other by 30 degrees. And the two planets are both quite massive. So how do you get such misaligned orbits rather than all the planets being in the same plane as in the solar system? Well, that's probably due to interactions with further out companions, and direct imaging will give us a chance to find them. The problem with direct imaging, of course, is that planets are faint compared to their stars. So this is in microns at different wavelengths, the brightness of planets in our solar system relative to the Sun. In the optical, Earth is almost 1 billion times fainter than the Sun. Jupiter is slightly better. Things get a little bit better in the infrared, but not a whole lot. So it's really, direct imaging is a big challenge because planets are intrinsically faint. And they actually fade away as they age. So it might help to target younger planets because they not only reflect light from the star but actually have their own thermal emission. When the planets are younger, because they're still accreting and contracting, they emit their own energy. And it's best to observe in the infrared. It gets a little bit better. But still, even in the best cases, it's usually about 10 to the 5 times fainter than their star. And they're right next to the star on the sky, typically within about half an arc second of the star. So it gets very, very difficult. The contrast is the problem. It's not only just that they're intrinsically faint, but they're next to a very bright source. So we really need to separate the planet from the star and also suppress perhaps the light of the star to be able to see a planet. Well, maybe this plot is a bit too complicated. Let's see. So this is the contrast between the star and the planet. This is around a typical solar type star. This is as a function of age. You can forget these two curves and just look at these in the near infrared. The main point is to show that the planets actually cool down and get fainter and fainter with age. So if you want to catch planets through direct imaging, it may really help to go when they're about 10 million years old, when the contrast is only about 10 to the minus 4, 10 to the minus 5, rather than when they're 1 billion years old, when the contrast is more like 10 to the minus 8 or greater. So really, for imaging, planets going for younger systems could really give you a leg up. The other thing that we need is, as I said, to separate the light from the light of a star, of the planet from the star. And for this technique called adaptive optics has really come into play. This is the technique where we use a deformable mirror as a secondary mirror in a telescope to correct for the distortions due to the Earth's atmosphere, which would otherwise blur the light of the star. So there are adaptive optics instruments mounted on the back of big telescopes, like Gemini in this case, that correct for that in a real-time way, and then you get a much smoother wavefront and be able to achieve much higher resolution. So, but even with adaptive optics, it's actually quite messy usually. This is an adaptive optics image of a star. You get all these messy speckles around it, which really don't help when you're trying to find a planet hidden in this mess. So you actually need usually to go even beyond that. I won't get into the technical details of that, of how there are various ways of suppressing these speckles. For example, subtracting the star from itself, letting the sky rotate during the night as you observe, and the star will rotate with its companion, and then subtracting the star from itself might allow you to see faint companions next to it. The other thing that could help is to go after low mass stars or even brown dwarfs. So brown dwarfs are objects that are too low mass to be stars, usually a bit more massive than planets, and they're much lower luminosity than stars, obviously. So here's a brown dwarf that's quite nearby, and right next to it, this European group led by Gershow and collaborators found a very faint companion. The brown dwarf itself is only about 25 Jupiter masses, and the companion turned out to be only about 8 Jupiter masses. So here's a planetary mass companion. It's not orbiting a star, it's orbiting a failed star or a brown dwarf. They were able to take a separate spectrum of the companion and indeed show that it's a cool object, low mass likely, and a year later they were able to show that it's actually moving together with the brown dwarf through space. So they're co-moving, likely bound system. We ourselves took a J-band image of this system. You can see the companion is a lot fainter at the slightly shorter wavelength of J-band. So it's a very red object. And here's a slightly better spectrum of the companion, confirming its low mass. We were able to show that both the brown dwarf and the disk and the companion have disks that are close to edge-on. Each of them has a disk. Well, are you going to call this the first extrasolar planet? Really depends on your definition. It's not orbiting a star. It's a planetary mass object. It's lower than what we call the deuterium burning limit. It's too low mass to burn even deuterium through nuclear fusion. But it's not orbiting a star. And given the mass ratio of only a factor of 3 between the primary and the secondary, the two almost certainly form like a binary star in miniature, rather than the companion forming out of a disk as we think planets form around a star. So it's quite different, but it's still interesting for the study of the objects of the companion's physics. So doing this kind of companion searches around stars is a lot harder because stars are a lot brighter. Sometimes you use occultation spots or various other techniques of suppressing the light of the star in order to be able to see these faint companions. As of a couple of years ago, there were no planetary mass companions imaged around stars. And then in 2008, in September, we announced this picture of a young sun-like star in the Upper Scorpius Association, about 5 million years old, with a companion that's pretty far out, about 2 arcseconds away, 330 AU at the distance of this star, that appeared to be faint enough to be a planet, and also had the right colors to be a planet. It was very red, and therefore we actually took spectrum of this companion right here and showed that indeed it's a very cool object in comparison to cool objects in the field, as well as in comparison to models. It's a very cool object, very close to a star, in a fairly loose association. The density of objects in this association is quite low, so we argued that it's almost certainly a planetary mass companion to this young star. It has a temperature of about 1800 Kelvin and a mass of about 8 Jupiter masses. The only thing, so at the time we announced that, we made news here in Sweden. I think Alexis was on a breakfast TV show talking about it. The only thing we didn't have at the time was that we had not shown that the two move together on the sky, so we hadn't shown that they're indeed gravitationally bound. And now, with observations for 2 years after that, over time, as the star moves through the sky, we have been able to show if it was just a background object, it would have moved like this, but indeed it hasn't moved differently. So with observations of 4 different epochs, we have a 5th epoch coming up in the next month, we've shown that these two are indeed have common proper motion. They're moving through the sky together, and we have a whole lot of other observations, including searches for additional companions in this system, and really confirmed everything we said almost 2 years ago now. And this is indeed a planetary mass companion to a young star, co-moving as far as we can tell. So it's very massive. It raises a lot of questions. How do you get an 8 Jupiter mass object forming 300 astronomical units away from its star? Did it get ejected? Did it form closer in and get ejected? Did it form as a binary stellar companion in some sense? It's an extreme binary companion. Its mass ratio is much greater. How did it come about is really raising a lot of questions. Now within, one thing we tried to do this fall actually, this connects to the talk I gave in the astronomy department 2 days ago, is we're trying to see if this is a directly imaged planet and it's far enough away from its star, we could actually monitor it to see if it's variable in brightness over time separately from the star. It's hard, but it's doable. And we just got time allocated actually a couple of days ago, along with Marcus Janssen, who's coming here next week, who's a postdoc in Toronto, working with me on this. We just got time this fall to monitor this object for about 6 hours to see, like Jupiter and like brown dwarf that show a lot of variability, whether this planetary object also has variability. If it changes, if it has clouds, asymmetric clouds, if it varies, we can measure its rotation period from the photometric period. So that would be very cool. The first time one can measure directly the rotation period of an extrasolar planet. Now, within about a month and a half of our announcement in September 2008, 2 other planetary systems directly imaged were also announced. This, I think, is actually the most spectacular one because it has 3 planets around the same star, HR 8799, imaged with adaptive optics on Keck and Gemini telescopes, led by Christian Marois and collaborators. And they had observations for 2 of them from 4 years earlier. They really could show not only are the planets co-moving with the star, they could actually see orbital motion of these companions in the same plane on the, relative to the star. At the time, they didn't have spectroscopy. These are models. But they had broadband imaging at a number of different wavelengths and showed at least the fluxes are consistent. This is how they derive masses for these objects. They're quite massive, just like the one that I showed you before at 8 Jupiter masses. These are 7, 10, and 10 Jupiter masses are the best estimates for these planets. These directly imaged planets, these are much closer range, 25, 40, and 70 AU. Relatively short periods, still fairly hot, have to be fairly massive and large. But what's cool about it is that there's orbital motion observed, so you can actually confirm that they indeed appear to be in the same plane, which is suggestive of a disk origin, right, forming out of a disk because they are orbiting in the same plane, even though they're quite massive, which again is challenging for planet formation models. My former postdoc, David Lafreniere, who was actually involved in that discovery as well, did an archival search in the Hubble archive and was actually able to recover the outermost planet of that system in a Hubble image from 10 years earlier, from 1998. So while we are going out building bigger telescopes, doing all this stuff, one could have, in principle, discovered the first directly imaged planet 10 years ago from publicly available images. Of course, it's easier to do that after the fact. You can go recover it than when you didn't know it was there. It was a fair bit of image processing on his part to do that. But what was nice about that again is that all of a sudden you had a 10-year baseline for the orbital measurement of the outermost directly imaged planet in that system, which is very, very neat, right? You can at some point start to get interesting dynamical signatures. And then on the same, actually in the same issue of Science where that paper was published, there was another announcement of a planet, a directly imaged planet around Fomalhaut B, which actually got the most press, partly because it was a NASA press conference, partly because it was in this beautiful image of a disk, a ring-like disk around this star Fomalhaut, which is nearby. And what they had was observations in 2004 and 2006 that showed movement of this speck that was consistent with orbital motion. Now, if you really challenge me, this is why you shouldn't be recording me, I would say this is the weakest case. Okay, here's why. So you have the specks, the other specks in this image. There's indeed orbital motion is nice. Well, at least it's consistent with orbital motion. But if you do any kind of comparisons to models, only at one wavelength do they use the flux measurement to derive a mass for this object. At the second wavelength in which it's detected, both are Hubble detections at these 2 epochs. At the second wavelength, the shorter blue wavelength, the flux has changed by about 30% between 2004 and 2006. Why would a planet do that? That's a huge change in flux. So, and it doesn't fit, neither of those fits. This is the model, right? Neither of those fits. And at the even shorter wavelength, they have an upper limit in the ground-based near-infrared at Keck and Gemini, at the methane band. They just have upper limits, no detections. So there's detections at just 2 wavelengths, out of which in one, it changed flux by 30%. Okay, and there's no spectrum, nothing like that. There's no chance of getting a spectrum for a long time because it's very faint. So, you know, I would take it, I mean, it's very intriguing. In fact, I would say the strongest case for it is because it nicely fits. It's consistent if you do dynamical models of what might be, you know, consistent with carving or kind of shepherding this ring of dust, then it's nice to have a planet there. It can do the job. Okay, so there was a companion paper by Eugene Chang et al. Which made that argument and really supported the idea that this is a real object. So how did they explain in the paper why is this flux so high? The explanation is that you're not just seeing the flux of the planet at the shorter wavelength, but also reflected light from a dust disk around the planet. But you know, I would say in science you have to be a little bit careful when you have 2 data points and you need an extra thing, a disk, to explain the second data point. Okay, I'm going to get in trouble for saying this, but this is, you know, it's obviously kind of at the cutting edge of science. You know, one can make, you know, it's very exciting. It's really fun, but it's also, you know, some things need, you know, could turn out to be different once you follow up. The unfortunate thing is this one is so tough to follow up because it's faint, but it's also, you know, quite interesting because of the directly imaged ones, it's potentially the lowest mass planet. It's still pretty massive, but it's pretty low mass. And then there was a companion announced in December of the same year, a candidate in the Beta Pictoris famous debris disk hidden along the same plane as that disk, was potentially a massive companion quite close to that star that was seen in images by this French team at VLT adaptive optics observations. They didn't, and I don't think they have yet, shown that the co-moving O has spectroscopy. So this one is really not a confirmed one, but it's an interesting candidate. Again, it's interesting partly because it could do interesting things to the disk. For example, there is a warp in the disk in the inner part, which if you had a planet embedded there, you know, would be a nice explanation as to how you get that kind of warping. So there's an interesting and exciting field where a lot has happened. There haven't been any announcements since then that I know of. There are a few low mass brown dwarfs found since then, but no planets.
How big was the blue chronograph in this left right-hand picture?
Okay, Alexis can tell you better than this. So this is the orbit of. What was the question? How big is this chronograph?
Mm-hmm.
Well, the inner part is not the chronograph, it's 2 images superimposed on each other.
Yeah. So to give you a scale, this is 8 AU.
Yeah.
Right.
So the range should be about 5.
And that's the same.
Yeah.
Oh, you mean in AU? How big is in AU?
Yes, but you can imagine, right? It's like 30 maybe or something.
Yeah. I mean, this disk is many hundreds of AU.
Yeah.
Okay, so it's really.
100,
yeah. I think this is actually. Yeah, exactly.
Mm-hmm.
I'm not sure this whole thing is a chronograph. This might be part after the fact that blocking all the mess just to make a beautiful image. So even though we only have a few systems, it's already quite interesting. It's, you know, revealed a whole new planet population, far out, massive, that were not known from any other technique. And at least in a couple of cases, there's evidence that they may be interacting with the disk. And then this 3-planet system is really challenging models. It's most interesting because there are 3 of them, and because we can make dynamical measurements of their orbits. And you know, do you have all kinds of other interesting things going on? I won't get into details of this just because I want to show you a couple of what's coming up next in the time that's left. As I mentioned, Kepler is up there and has announced 5 planets. They have tens of other candidates that are following up with radio velocity that they found first by transits. But many of the Kepler planets are on distant stars that are too faint to do a lot of follow-up. So complementary to that is this project done by David Charbonneau from the ground, where they have 8 telescopes in the same site in Arizona. They're looking one by one at the nearest 300 red dwarf stars, hoping to find transiting planets in some of them where you really can do a lot of follow-up because the stars are nearby, stars are bright, and they could potentially be habitable even if they're very close to the star because they're around red dwarf stars. And in fact, they announced the first one around a star called Gliese 1214 last December, and that has a mass of about 6 Earth masses, fairly big radius, close to 3 Earth radii, so it's relatively low density compared to the Earth. which could imply that it has a large gas component. It could be kind of a outgas super Earth. It could be a mini Neptune, kind of a scaled down version of an ice giant, or it could be it could have a very icy kind of planet with CO2 and a steam atmosphere. And what's interesting about this is that if you believe the models, you can at least distinguish between sort of two different possibilities. One which is a hydrogen helium rich large atmosphere, large scale height atmosphere, or atmosphere made of denser molecules that would be smaller in size. By making observations at two different wavelengths, if it's this kind of atmosphere, they would have very different fluxes during primary transit. Whereas if it's a more compact atmosphere, then at different wavelengths you would have the same sort of flux decrement during transit. And this is actually given the precision of the observations I showed you of secondary eclipse measurements we do for these giant planets. Our precision is good enough actually to detect this. So we've just got some trial data just last couple of weeks ago, and we actually also just got approved for an observing proposal this fall to actually try to do this from the ground. If it's down here, it's too faint for us to detect, so we can put an upper limit. But if it's an atmosphere like this, which is less exciting, honestly, for astrobiology, but at least we can rule it out, we could actually detect it from the ground. There's also an HST proposal, which I don't know whether it's accepted or not yet, by the discoverers, by Charbonneau's team, to try to do similar kinds of observations from space. But imagine doing a super Earth atmosphere detection from the ground, in the next few months. That's pretty exciting. So this is why having nearby, planets around bright stars could really give you a lot. In terms of imaging, there's two extreme adaptive optics instruments coming online at the VLT for the Europeans and Gemini South for the Americans and Canadians that are really going to do much better in direct imaging. So this is what we look forward to in the next year or so. These instruments will start to operate, and we can do much higher contrast, much better direct imaging searches. So that's when I really expect there to be, we have 3 or 4 now. That's when we expect at least a few dozen directly imaged planets to be known in the next 5 years, thanks to these instruments. If either of them or both of them work, we really should be able to do that. And then there's JWST, the successor to Hubble, to be launched in 2014, and that will really do wonders. So here's an instrument that I'm working on from the Canadian side for this telescope. Here's an image of a star without a coronagraph, with a coronagraph. Can you see the planets? No? Okay. We do a few tricks. We take observations at slightly different wavelengths, because these planets have certain absorption-emission lines in the spectrum. You take it on the peak, just off the peak, between two slightly different wavelengths, they pop out. And three different wavelengths, they really pop out. This is the 3-planet system 8799, a simulation of what we would see with this instrument. So this, you can really see. This is going to be doing nice things for planet imaging. And then in the longer term, the Europeans want an extremely large telescope. Canada is at the moment a partner in the 30-meter telescope project. And one of the main science drivers for both of these next generation of telescopes is really planet imaging. And there are already designs, for example, in Europe for an exoplanet imaging instrument, because this is where the action is. This is one of the most exciting things that these telescopes are supposed to do. So I'll end with just this plot, which is showing you the discovery of exosolar planets in the last 15 years. Starting in 95, these are the Plaza planets, and there was an object that probably is a planet that was found in 89, fairly massive object, and then 51 PEG. Most of the blue is still the radio velocity planet, so you can see the radio velocity technique really still dominates. The green is transits, which is a growing fraction of planet detections. And then microlensing and imaging are coming into play as well. But you can just see overall, the pace of discovery is still accelerating. Really, finding a planet is no big deal anymore, right? So the Geneva team, for example, makes announcements of planets. They announce 30 planets in one meeting, because that's the only way to even get a mention, even for people to turn their heads and say, "Oh, that's cool." Because one planet, unless it's really, a very low mass planet or something particularly exciting about it, is no big deal anymore. We're starting to think about populations and how do comparative planet Earth watch. So it's really an exciting field. I think it'll be set to continue at least for a little while. Thank you.
Mm-hmm.
Okay, Ray. So, a few questions?
Yeah.
You didn't comment on the Marcus Johnson's
spectrum.
Spectrum.
Yes.
It's,
Partly because you'll hear about it next week.
yeah, okay.
Partly because
You don't believe
you want me to be blunt? No, I believe it completely. You can't say a whole lot from it. That's the point. You can. The only thing he can really, because it's. I mean, if you see it, it's quite noisy. In a very broad sense, you can say it's a little. It seems a bit off from the models at the longer wavelengths. It seems it's somewhat inconsistent with the current plant models. But beyond that, you can't identify any features. You can't. So that's the only reason that I thought also he would give him a chance to tell you why. I mean, it is certainly an important step in this whole business, and it's something that I understand that another team actually. This is the middle planet of the 8799 system. For the outermost one, another team also apparently has a spectrum in hand now. So, but these are very, very simple, crappy spectra. So relative to, for example, right, this one, I mean, we can really see water absorption. We can really see all kinds of things in our spectrum. Because this is pretty far out from the star, it's pretty easy, right? So we have, I mean, this is decent signal to noise. You can actually identify individual absorption features, for example. So that's it. But I mean, he will have interesting things to say, hopefully, and also what the next steps will be. Yeah. Yes.
I have a kind of general question which I wonder if you want to comment on. And that's a problem, as I have understood it in these first 1.5 decades of discovery, has been the bias of the discoveries. And people have been very anxious to find planets, and therefore they have gone for, say, high metallicity.
Yeah.
And also solar-type stars have been very biased.
Yeah.
Now M stars are interesting. However, there are also K-type stars.
Yes.
My question is, are people doing this statistically properly now? And that is knowing their biases and trying to compensate for them in a kind of rational, systematic way.
Okay, so there are a couple of different things. One, so some biases are kind of unavoidable because of the technique, right? So for example, A stars, you can't really do radio velocity because they don't have enough lines and the lines are too broad. So some biases, unfortunately, are sort of unavoidable.
Although you could also compensate for that, if you know it.
Even if you know, but if you don't have lines, you can't measure radio velocity. So like something like that at some level is basically you can't. Except people are still trying in other ways. These A stars, once they evolve into subgiants, the atmospheres will be cooler and will have a lot more lines. So people are actually even trying to do higher mass stars with radio velocity by going after them at a later stage in their life. So people are compensating in that sense. So this wasn't meant to be an overview of all of exoplanets because it's too big a field to really cover. But one of the areas in which there have been interesting discoveries is actually in these higher mass stars doing radio velocity. If anything, they seem to have more higher mass planets around higher mass stars, and those samples are not big enough yet because for the solar type stars the samples are now 3,000 or so altogether. But for those the samples are still about 50 to 100. But it's starting to be interesting. And actually I had this one sentence in here that more massive stars may be more likely to have more massive planets. This comes both from direct imaging and from these studies. The other answer to it is that in terms of a full picture, this is sort of why I kind of kept emphasizing that I think you need all of the techniques, complementary techniques to get the full picture. Partly because each technique is biased to some extent no matter what you do, right? Now, the second level of bias which you're talking about, which is really going after solar type stars because we want an Earth, that is starting to change. And people are starting to do broader, for example, volume limited surveys in order to kind of take out that kind of intentional bias on the part of the researchers. So not any one group is going to give you that, but between all of the groups, I think the overall picture is starting to fill up. But the problem is, of course, you all want to get to lower and lower mass planets, right? So you need Kepler and you need Plato, as Alexis can tell you, the next version of Plato, improvement even on Kepler if you really want a true Earth around a solar type star that you can follow up. It's a challenge. So I think, with imaging too, right? We've really gone after young stars because that's where we know we'll get them. It's no point trying to do 100 old stars because we know we don't have the threshold. The detection threshold is not met. So you come up empty, right? So initially at least, yeah, you do go after what you can or have the best chance of doing, and then you come back and try to do the statistics.
Any other questions?
Yeah.
Have you looked at the possibilities of using VLTI to resolve
to some extent, I mean, so VLTI is, well, I mean, if you can take a direct image with adaptive optics, it's usually a lot better than what VLTI can do, right? Because unless you do a whole lot of different baselines, you don't get an image. You get an asymmetry and you can tell there's something there. So in some sense where you can do AO and take a direct picture is usually a bit stronger. But VLTI could be better for trying to get closer in than we can. But it's not only getting smaller and smaller angular resolution, but also the contrast, right? So it's not that easy. I mean, it seems that VLTI might actually do better in some sense also doing astrometric planet searches.
There was at some point an agreement between ESA and ESA to make a knowledge astrometry of the VLTI, but I think that these efforts were sort of implemented that.
It's very hard from the ground. So I was involved in one of the science teams doing using the nulling interferometer on the two CACs. Okay, we're doing nulling at 10 microns looking for dust disks. The nulls that are actually achieved at the telescope is not enough. It's more like 100 is achieved quite routinely, maybe 1,000 sometimes. But even for the most massive planets, you need a null of more like 10,000 to 1. And that's very hard to achieve with the Earth's atmosphere. So they've demonstrated it in the lab. They've achieved incredibly high nulls, actually almost high enough in the optical. I write about this actually in my popular book. Westraub and what's his first name? Traeger did an experiment in a single monochromatic light. They achieved a null good enough to detect an Earth-like planet, that kind of contrast. But that's in the lab at JPL, and they think they can do that in space. But from the ground, it's very challenging. So far, VLTI has been good at some things like measuring sizes of nearby M-dwarf stars directly, for example, which is really relevant for what we do, right? Because we make all these comparisons to stars thinking we know the stars, but we don't know them well enough. It's good for various things. So far, I don't know of any, and it has done interesting things with circumstellar disks, both Keck and VLT interferometers. But for direct imaging, it hasn't quite gotten there. And I'm not an interferometry expert, so my guess is that the limitation would be the contrast. And also the star. Oh, the other thing I forgot to mention is that usually you need the primary star to be incredibly bright, right? So that limits your sample.
Yeah, but they are looking at bright stars. I mean, that's.
Are you looking at stars as bright as 6 magnitudes?
no, but for the interferometer, people are actually looking at going to 16th magnitude or so. The gravity incident, for instance, is designed to do that. So, I mean, if I'm looking at Kepler and coronal stars, it should be possible.
Kepler and coronal stars?
I would think so.
I don't think so.
With the next generation.
Oh, with the next generation, yes. Yeah, but not the current instrument.
No,
yeah, exactly.
Okay, so we will have a few snacks and drinks outside here, so you're welcome to stay and talk to Ray, ask you more questions.